We only see certain colors emitted from the hydrogen lamp. We don't see all the colors of the rainbow, do we? Otherwise, we would have seen white light. And so what this means is this. This means that there's only one color of red allowed. And so that red light that you see is from an electron getting excited into this red region here, and then dropping back down, and then emitting the red light here. But what it implies is, it implies that none of the other colors of red are allowed. And so what we see is that we can only excite the electron to this energy here. And so we call this an allowed energy. But all these, like say if we wanted a different shade of red, that would be forbidden, or another shade of red, that would be forbidden. The next allowed energy is we have to excite the electron all the way up to the green. And so here, everything's forbidden. So orange, yellow are all forbidden. And then when you get to the green, this is allowed. And so we get green light being emitted here. And the same thing. All these energies between green, this shade of green to this shade of blue are forbidden, and then once we hit a certain shade of blue, that's allowed. And so the strange thing is this. What these light patterns tell us is all these energies here are forbidden. Forbidden energies. In other words, the electrons cannot get excited to those energies, otherwise we'd see the light of those energies coming off. Whereas in the metal and in the sun, the electron can get excited to any energy it wants. And so what we call this is, we call this an unusual light pattern. It's unusual in the sense that it's not what we expect. It's an unusual light pattern because when we excite electrons, we should be able to excite them to any energy we want. Now for the hydrogen atom, what does that imply? Well, that implies that we can't have, this is the classical physics thinking. Classical physics thinking is we can't excite it to any orbit we want. And so what happens is we'll have one orbit, this is allowed. And then we'll have a region where it's completely forbidden for that electron to orbit. And so this would be forbidden. Although, and then out here will be allowed. And then a whole range of forbidden. And then again, we'll have an allowed. And so what happens here is you can't just excite the electron a little bit. If you could excite the electron a little bit more than here, then we should emit these colors. And a little bit more, a little bit more, a little bit more, a little bit, no. What you have to do is you have to excite the electron all the way to the next step, which is out here. And then excite it again all the way to the next step out here. In other words, there's jumps in the energy or gaps in the energy here. And so we have a different way we discuss these things. This line here is what we call a continuous spectrum. In other words, the energies are continuous here. Over here, this is called a line spectrum. In a line spectrum, it's discontinuous. In the line spectrum, what we have is we have what we call quantized energy level. All quantized means is this, the quantized means not continuous. Well, continuous means you can have any increment you want. And so if we're looking at elevation on a ramp, you know, this is continuous here. Continuous in the sense that if I'm climbing up in elevation, I can stop anywhere on this ramp and have any, you know, gravitational potential energy I want. But if you're taking an elevator, can you have any gravitational potential energy you want? No, because we're going to have a first floor, a second floor, a third floor. And so let's say I don't want to stop at the second floor, I want to stop at the 2.25 floor. Is there such thing as a 2.25 floor in a building? No. And so the floors of the building have quantized gravitational potential energy, whereas if I look at a ramp, that would have continuous gravitational potential energy. And so what we're saying here is this. We're saying that the electron energies aren't continuous. Because if they were continuous, we'd get all the colors of the rainbow. And so in other words, the electron energies are what we call quantized. Or discontinuous. Now the big question is, you know, why are they discontinuous? Why can't the electron orbit anywhere it wants to orbit? You know, you just give it a little bit more kick, and it should orbit just a little bit farther out. But it doesn't happen. And so why do we have so many forbidden regions here and only distinct allowed regions? And so this is very unusual because this was a observation that couldn't be explained by classical physics. And so let's look at some other atoms that show this discontinuous energy. Discontinuous energy is like the hydrogen atom. And some of these are a bit more complex. And so what you're going to do is you're going to go around, and you could either use the LabQuest or the handheld. Maybe the handheld's a little easier. And then just take a look at some of the other excited atoms we have in here. We have, what else do we have? We have hydrogen, we have helium, we have neon, and we have sodium. Sodium's over here. And so sodium would be like a street lamp. And so what you're going to do is you're just going to go around and then take a look at these, and then we're going to start talking about Chapter 8. So I'm going to flip off the lights here. Just turn on the lamps. Walk around and take a look.